Hello, Heritage Academy geometry students, and welcome to another fascinating geometry lesson brought to you by Mrs. Elzagary, PowerPoint, and of course, the internet. This lesson is lesson 2.2. That is chapter 2, lesson 2. You can find this lesson in your book on page 46 and 47. Don't forget to fill out your Cornell notes while we're going through this lesson and use your textbook to help you as well. We bought it for a reason. All right, let's get going. So in our previous lesson, we discussed logic, and we discussed that logic is a way to think critically. And in fact, it's defined as the art and science of critical thinking. So how does this affect us in math? What does this have to do with geometry? Well, throughout chapter 2, that's what we're going to continue to explore. Now, before we go any further, let's talk about ultimate objectives for chapter 2. So we know our God is a logical God and that the Bible is filled with examples of how he put things into a perfect, sound order. So God has a logical plan for each and every one of us, but because he's given us this ability to reason using logic or critical thinking, he expects us to learn about, practice, and use this gift that he has only given to people. Now, our intermediate objectives, which apply specifically to lesson 2, have to do with understanding and writing conditional statements and their converses, and kind of exploring if these conditional statements are true and also if those converses are true. We're going to go a little bit deeper into this idea as well, that when we do have a true converse, then we have something that is A, if and only if B. And when we have a situation like this, where both the conditional statement and the converse are true, we have something called a biconditional statement, and we have a special way to write that. So this is lesson 2.2, definitions, pages 46 through 47. Recall from our previous lesson, we learned that conditional statements can be changed into a converse, which is where we exchange the hypothesis and the conclusion, we switch them. We can make it into an inverse, where we take the conditional statement, but we make the hypothesis and the conclusion negative. Or we can also make it into a contrapositive statement, which is where we're going to make the converse and then also make it negative. And you can see those symbols on this chart are different than what we see in our book. Our book is going to use A and B, but we discussed how in other math classes, sometimes in traditional logic, you'll see other letters being used to represent the same concepts. So lesson 2 starts us off with a rancher who got himself into a little bit of trouble over an argument about the actual definition of a horse. And you can read about that on your own, but it's a pretty interesting story. I would encourage you to take a look at it closer on your own time. But the idea behind this is that we have to be very careful and clear in our definitions, and this especially applies to math for our purposes. So if we look further down that page, we can see that starting about here, it says, disagreements about the meanings of words frequently come up in courts of law. To prevent arguments and debates, key terms are often defined first. Variations in a word's meaning seldom cause much of a problem in everyday communication, but they're serious when we're trying to reason precisely. For this reason, definitions play an important role in mathematics. So when we define a word in geometry, the word and its definition are understood to have exactly the same meaning. For example, when we define a triangle as a polygon that has 3 sides, we can say not only that if a figure is a triangle, then it is a polygon that has 3 sides, but also if a figure is a polygon that has 3 sides, then it is a triangle. Notice that the hypothesis and the conclusion of the first statement are interchanged in the second. The second statement is called the converse of the first. The converse of a conditional statement is found by interchanging its hypothesis and conclusion. In symbols, the converse of if A, then B is If B, then A. So let's explore truth in statements and definitions. An example of a statement might be, it is a whodunit if it is a detective story. And you've all probably heard that term, a whodunit. And if you haven't, it is a detective story. So our hypothesis is if it is a detective story, which is our A portion. Notice that it comes as the second clause in our statement, which means our conclusion is it is a whodunit. So let's put this into an actual conditional if-then statement. If it is a detective story, then it is a whodunit. Now let's make it a converse statement. If it is a whodunit, then it is a detective story. When we're looking for truth in statements and definitions, you want to ask yourself, does the converse mean the same thing as the conditional statement? If the converse means the same thing as the conditional statement, then the statement is in fact a definition. So let's explore these definitions in detail. For our conditional statement, if it is a detective story, then it is a whodunit. Remember our converse, if it is a whodunit, then it is a detective story. So from this, we can deduce that a whodunit and a detective story are the same thing. When the conditional statement and converse are the same thing, which is of course a definition, we can denote this in the following ways. We can use an A with a B, and notice the double arrow in the middle, which reads A if and only if B. But the other way to write this is A if B, and notice the two F's. Those two F's standing for if and only if. So let's explore this concept of if and only if and the biconditional statement. A biconditional statement is combining a hypothesis and a conclusion in a conditional statement using if and only if to connect the clauses. So if our conditional statement reads, if it is a detective story, then it is a whodunit, our biconditional statement reads, it is a detective story if and only if it is a whodunit. You can replace if and only if with if, the double F. It is a detective story if it is a whodunit. So let's put this into practice. You can pause throughout this slide to practice writing some of these statements on your own. So here's a statement to try. A triangle is a polygon that has 3 sides. Try writing the conditional statement. Did you get something like, if it is a triangle, then it is a polygon that has 3 sides? If so, good, you're on the right track. The hypothesis is if it is a triangle, and our conclusion, then it is a polygon that has 3 sides. So try writing the converse. Did you get something like, if it is a polygon that has 3 sides, then it is a triangle? Ask, is the converse of the conditional statement true? Yes, then you have a definition which can make a biconditional statement. So here's where that logic comes in, and you have to think about the truth in your statements. So this can look like a biconditional statement by writing it, it is a triangle if and only if it is a polygon that has 3 sides. And notice we used IFF for if and only if. So try this guided practice, and I would encourage you to pause every so often and try doing some of these things on your own and then pushing play and checking your answers with mine. This example comes from set 1 on page 47. All geese have 2 legs. So here's a statement that we can make into a conditional statement. So go ahead and try that. Did you get something like, if it is a goose, then it has 2 legs? If so, good thinking, you're on the right track. Now it's still important to identify our hypothesis and conclusion. So try that now. For our hypothesis, you should have gotten something like, if it is a goose. And your conclusion, then it has 2 legs. So now let's practice putting this into a converse. If it has 2 legs, then it is a goose. Ask yourself, is the converse of the conditional statement actually true? Now let's think about this. If something has 2 legs, does it have to be a goose? No, people have 2 legs. There are other creatures out there that have 2 legs. So notice that in this case, the converse of your conditional statement is not true. So this means that we haven't really made a definition for what a goose actually is. This also applies to the idea of if and only if. We can't make a biconditional statement using if and only if for the original statement, all geese have 2 legs. It's just not enough to give us a definition. So finally, let's use Euler diagrams to help us determine whether or not a conditional statement is in fact a definition. So recall our statement about triangles and polygons with 3 sides. If we start with our first statement that if a figure is a triangle, then it is a polygon that has 3 sides, we can put triangle here in our first circle, and polygons with 3 sides goes in our second circle, our larger circle. Notice if we switch those and write a converse, we can say if it is a polygon with 3 sides, then it is a triangle. Here, we can switch our A and B, or our hypothesis and conclusion, but we can actually still see that they mean the same thing. So we have a definition. But try the other example with the goose and the 2 legs. If it is a goose, then it has 2 legs. That is what our first Euler diagram is showing us. But when we switch into our converse statement, when we said if it has 2 legs, then it's a goose, we found that that just wasn't true and didn't work, because certainly there are other things with 2 legs that are not geese. Make sure that you read through pages 46 and 47 on your own. Go back through this video if you need more support, and finish writing those Cornell notes and get that homework done. Here are a few additional resources to help you out. Good luck. Let me know if you need support, and I will see you in class next time.